We have extended the capabilities of the Linear Temporal Logic Mission Planning, or LTLMoP, framework to control modular robots. With this toolkit, we can control robots by defining a task specification in structured English or linear temporal logic. This specification is then synthesized into a correct by construction automaton. In turn, the robot is controlled in continuous time while obeying the automaton using a hybrid controller. We have enriched the grammar of LTLMoP in order to incorporate reconfigurable modular robots. We are now able to use traits such as fast and narrow to describe different modular robot morphologies that complete different parts of a task specification. For more information, refer to the website below, LTLMoP.github.com.
Traits are incorporated into high-level control by using a library. This library has a list of all traits as well as the configurations or gaits that match each trait. For example, the trait tall has been assigned to the configurations foldover, biped, and slinky. The library takes a set of traits as input and outputs any configuration gait pairs that satisfy these traits. When we specify traits in LTLMoP, the library will automatically find a configuration gait pair and reconfigure the modular robot when necessary to satisfy a specification. LTLMoP without traits is guaranteed to construct a correct automaton. If there is a configuration gait pair for every state, the automaton can be successfully synthesized, provided that the rest of the task specification is realizable. Let's analyze a simple correct specification. The robot is set to visit regions R1 and R2. If the predator sensor is activated, so is the trait fast. If the robot is in region R2, the trait 1D motion is activated. This schematic shows the automaton for this specification. Because each state of the automaton must have a configuration and gait, we have developed a gait checker algorithm to guarantee correctness. Upon compilation of a task specification, we check every state where a set of traits are specified to see if there is a corresponding configuration and gait that satisfies that set of traits. If there is a trait that does not exist, a compilation error will be thrown. In this example, we use the trait slow, which does not exist in the library. A warning is shown saying that there is no such trait, and all the states of the automaton with the trait slow violate the specification. If there is no corresponding configuration gait pair for a set of traits, an error will also be thrown. In this example, the automaton has one state where holonomic and fast are active at the same time, and one state where holonomic, fast, and stationary are active at the same time. Both of these states violate the specification because the library cannot find configurations that satisfy these trait combinations. Also, if there are no traits specified in a state, the robot uses a default configuration.
To begin with, we will show an example using a simulated robot. The map of the simulated environment and the task specification in structured English are shown here. We will highlight some of the main characteristics of the specification. The robot is set to start in the island region at the upper left of the map. It must avoid the regions Water, Water 2, and Water 3. If the robot is not sensing anything, it will navigate between the dock and meadows regions. When the robot's poison sensor is activated, it will instead navigate to the springs region until poison is no longer sensed. The traits slow and non-holonomic turning are activated in the tunnel region. The traits fast and 1D motion are activated in the bridge region, which is located between the island and the dock. The robot must stay still if the predator sensor is activated. The trait stationary is activated when the prey sensor is activated. The robot's default configuration is a hexapod configuration, but in the initial region it is set to the snake configuration.
Now we will show the simulation of the task we just described. Here is an image of the desktop. The physics simulator of the CKbot modular robot is in the right window. The sensors are push buttons on the left side of the screen. A red button denotes that a sensor is off, while a green button denotes that the sensor is activated. Finally, we have the map in the background. Notice that the color of those regions are also mapped onto the ground in the CKbot simulator. The robot starts an island. It progresses across the bridge so that it might go to either dock or meadows. On the bridge, the robot changes gait and configuration so that it moves fast and straight as specified by the traits fast and 1D motion. Now that the robot is not in bridge, it has resumed its default configuration of hexapod. The predator sensor is now activated, so the robot must stay still. Now the predator sensor is no longer activated, so the robot can continue moving. The robot senses poison, and so now it must go to springs. It will stay in springs until the poison sensor is no longer activated. prey is now detected, and so the robot reconfigures to a plus configuration so that it can capture the prey. The robot now continues onward toward meadows. Because all sensors are deactivated, the robot can continue to dock or meadows, but it will choose meadows in the simulation run. When the robot reaches tunnel, it reconfigures to a snake configuration with a crawl gait so that it can stay low with non-holonomic turning, as specified by traits. The robot will next reconfigure to the default gait and continue to move.
Next, we will show a different example with the CKbot modular robot. The robot is set to start in the plains region. If the robot is not sensing anything, it will navigate between the plains and plateau regions. When the robot's burn sensor is activated, it will instead navigate to the springs region until burn is no longer sensed. The trait stationary is activated when it is sensing burn and is in the springs region. The robot must avoid the lava 1, lava 2, and lava 3 regions. The traits low and narrow are activated when between lava 1 and lava 2. This region is the white rectangle in the center of the map. When the landslide sensor is activated, the robot must stay in place. The robot's default configuration is the T configuration. Because reconfiguration with CKbot is not instantaneous, the different configurations we use for this example are just different sets of motion gaits. The snake configuration turns by moving its head module left to right. The T configuration, unlike snake, also uses the two tail modules for locomotion. The T swim configuration is not designed for locomotion and is used as a stationary configuration. Here we see the T configuration using the tail modules to turn.
The hardware is now shown performing the specification. An image of the field is shown. Note that the starting region, plains, is now in the bottom left-hand corner. The robot starts in plains and heads toward plateau. A landslide is sensed, so the robot stays still. The robot then continues toward plateau using the default gait. Between lava 1 and lava 2, the robot changes gait to the snake gait. Outside of this region, it will change back to the T gait, which is the default gait. The burn sensor is now activated, so the robot moves toward springs. While the burn sensor is activated and the robot is in springs, it uses a stationary gait, which is in this case the swim gait. When the robot is no longer sensing burn, it can then continue onward to plains or plateau or otherwise continue to follow the task specification.